Welcome to lesson 21. In this lesson, we will continue with the power flow problem. In this lesson, we will first take up power flow problem for large power systems. How do we implement it? What are the implementation aspects? One of the aspects which we will look at will be sparse matrix methods and its application to power flow problem, and then we will also look into the modeling of regulating transformers in power flow problem. On the completion of this lesson, you should be able to explain the issues involved in implementing power flow solution for large power systems, apply sparse matrix methods to power flow, and develop regulating transformer model for power flow solution. Now, what are the types of power flow methods that we have learnt earlier? We have discussed about the Gauss-Seidel method for solution of power flow problem. Then we looked into the NewtonRaphson method. Then we tried to take advantage of the physical property of the power system, where the real power and voltage phase angle close association and reactive power and the voltage magnitude close association was taken into account, and the power flow equations were decoupled into P delta and QV two sub problems. And then we saw that by taking certain physical characteristics of the power system, we can modify the problem into what we call the fast decoupled load flow problem, where the Jacobian matrices used become constant. That is, we have the B dash and B double dash matrices, which are basically similar to the susceptance elements of the Y bus matrix, and therefore, they remain constant. So, we would like to see out of these four different methods, which method would be suitable for large power system problems. We had seen that the Gauss-Seidel algorithm is the simplest The Gauss-Seidel algorithm is the simplest algorithm and requires minimum time per iteration, because the computation involved is much less, though we have to do this computation in the complex frame, that is, all quantities power, voltage and admittances are used as complex quantities. However, one problem encountered with the Gauss-Seidel method is that the number of iterations for Gauss-Seidel algorithm increases with the system size. That is, if you are working for a smaller system, the number of iterations required for convergence is going to be small, but if you are working with large system, then this number of iterations for same accuracy of convergence is going to be very large. And this is one of the main reasons why Gauss-Seidel method is not suitable for large power system power flow applications. In fact, Newton-Raphson method was known earlier, but this method could not be used for power flow problem, mainly because for large system it required large Jacobian matrix solutions, that is solution of large system of equations, which was not possible earlier. That is, Newton-Raphson algorithm requires large storage for the Jacobian matrix. Also, the computational requirement per iteration is high, because Jacobian elements have to be computed at every iteration. Though this is somewhat complex, but a major advantage of Newton-Raphson method is that the number of iterations required for convergence is independent of the system size. That is, normally it will take around 3 to 5 iterations for convergence, even for very large systems. NL algorithm is somewhat complex to program. However, it uses the real and reactive power equations separately, that it deals with real numbers, it does not deal with complex numbers. That is, all quantities used in Newton-Raphson method for power flow are real numbers. We do not work with a complex number in case of Newton-Raphson power flow. Another method is a very reliable and accurate method, and therefore, is the preferred method for large system power flow applications. That is, most of the commercial programs for power flow use Newton-Raphson algorithm for the solution, and people have solved problems of more than 10 to 20,000 buses using Newton-Raphson method of power flow. The other method which we talked about was decoupled method, but decoupled method has some convergence problems, and therefore, this is not very much in use, but a variation of the decoupled method, which we call the fast decoupled method, is very much in use, because it requires much less storage than the Newton-Raphson method. Actually, since we have decoupled the real power and the reactive power equations, that is real power P delta equations and QV equations. Therefore, we have two subsystem equations, one dealing with real power and voltage angle, another dealing with reactive power and voltage magnitude, and the size of the matrices, that is B dash and B double dash, are much smaller, that is they are almost half the size of that of the Newton-Raphson method. That is, if Newton-Raphson method for n bus system requires 2n into 2n size of Jacobian matrix, B dash and B double dash matrix are going to be smaller than n is to n matrix. The algorithm is simpler to program than the Newton-Raphson method. Again, this is mainly because the Jacobian element calculation is no longer involved here. The matrices B dash and B double dash are basically the susceptances of the Y bus matrix, the susceptance elements of the Y bus matrix, and therefore, much simpler to compute. Fast decoupled load flow method requires much less computation as compared to Newton-Raphson method, because B dash and B double dash matrices are constant, and therefore, they need to be factored only once. Whereas, in case of Newton-Raphson method, you have to compute the Jacobian matrix in each iteration and then factorize it in every iteration for finding out the updates for voltage, magnitude and phase angles. Whereas, in case of fast decoupled, we do not have such a situation, since B dash and B double dash matrices are constant, they can be factored and stored once for all the iterations. Number of iterations for fast decoupled load flow also is not very much dependent on the system size, but is somewhat larger, that is about 6 to 10 iterations are required for solution of large power systems. So, though the number of iterations required here is somewhat larger, the computation involved per iteration is much less. Therefore, the time taken by fast decoupled load flow method is considerably less than that for the Newton-Raphson method. Similarly, though the computation for Gauss-Seidel method is much simpler and computation per iteration required is much less than that of Newton-Raphson method, but because the number of iterations required are very large for convergence, finally, the time or the computation time for the Newton-Raphson method for large systems is smaller than that of Gauss-Seidel method, and this is the reason why Newton-Raphson method and fast decoupled method are very popular for power flow solution of large power systems. Now, both Newton-Raphson and fast decoupled load flow algorithms require the solution of matrix equation of the type A x is equal to b of large dimension at each iteration. This is the major problem that both these methods face, that they need to solve a large set of matrix equation of the type A x is equal to b, where A is a Jacobian matrix or B dash matrix, B double dash matrix in case of fast decoupled load flow. X is the vector of unknowns, that is voltage magnitude and voltage phase angles, and B is the mismatches, that is delta p and delta q. So, we need to solve this kind of a equation A x is equal to b at each iteration, and for large size system the size of A matrix is going to be very large, and this has been the major problem in implementing these methods, that is Newton-Raphson and fast decoupled method for large power systems. But one advantage that we take from the physical structure of the system is that in a large power system, on an average fewer than 3 lines are connected to each bus. That is, each bus will be connected to maybe 2 or 3 other buses in the system, which simply means that on an average less than 4 non-zero elements are there in each row of Y bus matrix. That is, Y bus matrix contains only 3 to 4 non-zero elements in each row. That is, if we take a 1000 bus system, then we have only about less than 4000 non-zero elements in the Y bus matrix, instead of 1000 into 1000 elements in a 1000 bus system Y bus. That is, instead of 1,000,000 elements, we have only 4000 elements, that is the Y bus has almost 996,000 zeros present in it and only 4,000 non zeros for a 1000 by 1000 Y bus matrix. Such kind of matrices which have very large number of zeros in them are called sparse matrices, and knowing this property of the Y bus of the system, we try to take advantage of the sparsity of the Y bus matrix in solution of the power flow problem. Let us see how we do this. So, what we have, the matrix Y bus matrix with very few non-zero elements is present, and it is a sparse matrix. Now, if we store this matrix as a two dimensional array, that is having elements a I j in a matrix of I in a matrix of 1000 rows and 1000 column for a 1000 bus system, we store these non-zero elements only. The zero elements are not stored, but if we need to store only non-zero elements, we need to know which elements of the matrix are non-zeros. That is, we need to identify these non-zero elements with their row and column numbers, and therefore, we need to prepare a kind of a linked list. That is, instead of storing the Y bus elements as a two dimensional array, they are stored as a linked list of elements to save computer storage requirement. So, this way if we store them as a linked list, then we will save large amount of computer storage. Similar is the case for the Jacobian matrix, because if we recall the elements of the Jacobian matrix, they contain y I j element, and if y I j is 0 for any I n j, then H I j submatrix, M I j, N I j and L I j submatrix will also, those elements H I j element, M I j element, N I j element and L I j element will also be 0 for these matrices. Therefore, compact storage using linked list can be used for storing the Jacobian matrix elements as well. Now, let us see compact storage as a linked list for a 1000 bus system with 100 PV buses. What will be the number of elements in a Jacobian matrix for such a case? Now, considering average of 3 lines connected to each bus. So, this will require storage of less than 16,000 elements as compared to about 4 million elements in the Jacobian matrix for a 1000 bus system. Because here each of these matrices H, M, N and L will be having only about 4000 or less elements. Therefore, the total number of elements, non-zero elements in this system will be only of the order of 16,000 as compared to 4 million. For fast decoupled algorithm, the storage requirement is even less, because we need only B dash and B double dash matrices, and the size of both these matrices are going to be 1000 by 1000 or less. For the PV bus, B double dash matrices will not have any equations, therefore, they will be having a size of only 900 by 900 for a 100 PV bus system. Therefore, the elements there are also going to be less compared to B dash elements, and the total size or total number of elements in B dash and B double dash will be less than 8000 elements only. So, how do we store these elements as a linked list? Let us for example, take a very small 4 by 4 matrix A. So, A is given here as shown. The diagonal elements are 1, 2, 3 and 4. The off diagonal elements are 5, 6, 7, that is A12 is 5, A13 is 6, A14 is 7, A21 is 8, A23 is 0, A24 is 9, A31 is 10, A32 is 0, A33 is 3, A34 is 0, and similarly A41 is 11, A42 is 0, A43 is 0 and A44 is 4. Now, how do we store this matrix as a linked list? Let us see what we do. We create 4 arrays. One we call as CE, the compact storage elements. This array is a single dimension array and contains all the non-zero elements of the matrix as stored in a serial order as they are in the rows. So, we have 1, 5, 6, 7, then 8, 2, 9. So, this is 1, 5, 6, 7, 8, 2, 9, and after this we have 10, 3, then 11, 4. Then we have 10, 3, 11, 4. Now, this array ICL is an array of integer numbers. It identifies the column number for these elements, and the size of this array is same as the number of non-zero elements in the matrix. So, ICL corresponding to the first element is 1, indicating this is in column number 1. The element number 2, which is 5, is in column number 2. So, ICL is 2. Similarly, the third element is 6 and this is in column number 3. The fourth element is 7, this is in column number 4. The fifth element is 8, fifth element is 8 and this is in column number 1. So, we have fifth element which is 8 in column number 1. Then sixth element is 2 which is in column number 2, seventh element is 9 which is in column number 3. I am sorry, this should be 4 in column number 4. Then eighth element is 10 which is in column number 1, sorry, eighth element is 10 column number 1, ninth element is 3 which is in column number 3, 10th element is 11, this is in column number 1, 10th element is 11 and this is in column number 1, whereas 11th element is 4 and this is in column number 4. So, 11th element is 4 and this is in column number 4. We have another array, again an array of integer numbers which is of the size same as the number of non-zero elements, and this is a very interesting array. What we do in this array is indicate the column number or the serial number of the next element in the same row. That is, if we see C is 1 and the next element is in position 2. So, and for the same row. So, if we see here, we have 1 and then we have 5 as the next element, then we have 6 as the next element, and then we have 7 as the next element. After this, the row ends. So, if we see here what we have, for the first element we have 1 and the next element is the serial number 2 element is found in serial number 2, and again for this we have indicated 3 here, because the next element after this is found in serial number 3 position, and for this element the next element is found in position number 4. So, position number 4 has 7, which is again an element in the same row. Now, after this 7 there is no further elements in the same row. So, the next element is no longer there for the same row, and this is indicated by a null pointer, that is by 0. So, this 0 indicates that there are no more elements in this row. So, this row ends. Now, again if you look at the second row starting, we have 8 in the column number 1, and what is the next element to this? The next element to this is in position number 6. So, we are putting 6 here, and the next element in position number 6 is 2, that is 2 2, that is for the same row here, and again for this, what is the next element? The next element is in the same row is 9, and this is at position number 7. So, we have for this next number as 7. So, 7th position number 7 we have this element. Again the row ends. So, then there is no next element, and this is indicated by a 0, and then again we take the start with the third row, and we have the next element at position number 9 for this, and then after this 3 3 we do not have any element 3 4. So, the next here is indicated by a 0, and so the next row starts, this is 4 1 element, and the next element here is in position 11 as indicated by the NXT for this, and here this is the 11th element, and again after this we do not have any element. So, that is indicated by null pointer 0. So, this now one question comes, why do we use this array next? We will see later when we talk about the elimination process, that while doing this elimination we will get some fill-ins, that is some of the elements which were 0 in the original matrix will now become non-zero, and since we cannot store them again at their requisite position in the matrix, that is, if we see here, if this element becomes non-zero, then what happens is we need to store that. Now, here we do not have any space for storing this. So, this has to be stored only at the end. So, when we store this at the end, what will happen is that we will have to indicate that number, that is, this element is coming after this 2. So, below this 2 we will have to indicate this next instead of 7 as 12, and this element can be stored here, and then below that for the next will be 7 which is stored here. So, this next is able to make us store non-zero elements which come as fill-ins during the factorization process. We have another row here, or row vector, which stores this. This is an array of integer numbers again, and this array is having a size which is equal to the size of the matrix, that is, it is a 4 by 4 matrix. So, there are going to be 4 elements in this. And what does this say? This array tells us the row number 1 starts at position number 1, row number 2 starts as position number 5, row number 3 starts at position number 8, and row number 4 starts at position number 10. So, if we want to work on any particular row, we can directly, using this I row, we can directly go to that starting point of that row and work with that row, instead of going through the complete sequence of all the rows. So, this again is very useful for the factorization process. So, this is how we store the elements. Now, if you look at this 4 by 4 matrix, you will say that we have not saved any memory, because what we have done is, instead of 36 instead of 16 elements that we have in that matrix, we are storing 11 real numbers and 22 plus 4 26 integer numbers, which itself will be a large storage, which is more than the storage required for 4 by 4 matrix. But if you look at a 1000 by 1000 matrix, then instead of storing 1,000,000 elements, you will be storing say 4000 here and 4000 for these two, as integers require half the number of bytes as the real numbers. So, 4000 plus 4000 8000 plus 1000, that is again half the bytes for the real numbers. So, around 500. So, 8500 real number bytes are required only. So, instead of 1,000,000 into 8 bytes, if we store the real numbers as double precision numbers, then we require 8 byte for each real number. So, 8 into 1,000,000, that is 8,000,000 or 8 megabytes will be required for a 1000 by 1000 matrix, whereas for this sparse matrix you will require 8 into 4000, that is 32,000 plus 4 into 1000, this is this will be 4000, yeah. So, 32,000, this will be again 32,000, 64,000, and this will be 4,000. So, 68 kilobytes only, as compared to how much? 8 into 8,000,000, 8 megabytes. So, this is the advantage that we get in case of large matrices. Now, let us see if we do the factorization for this kind of a matrix, what happens. Now, if we take a matrix like this, that we have used earlier, the same matrix, and if we try to use the Gauss elimination method for factorizing this matrix, then after the first step of Gauss elimination, that is reducing all the elements in the first column as zeros, what we will have is all these elements which were 0 are now getting filled in. That is, instead of a sparse matrix, now we have a completely full matrix. That means sparsity is lost because we get large number of fill-ins in this case. Now, let us see what we can do about it. So, if we are trying to take advantage of sparse matrix and we want to use this sparse matrix method, if we go through the factorization just like that for the given matrix, then we find that the sparsity is no longer maintained because large number of fill-ins will come. So, what do we do to minimize these fill-ins? So, to minimize these fill-ins during the reduction step, the matrix needs to be reordered or renumbered according to the number of non-zero elements which in each row, which we call the row's valence. So, if we take any row and see how many non-zero elements are there in that row, and we call that as the row's valence. So, if we pick up the rows which have minimum number of non-zero elements, or the rows with minimum valence are ordered as row number 1, and so on we go till we reach the last row which will have the largest number of non-zero elements. So, if we try to use that starting with the minimum valence node, for the given example the numbering should be. Now, if you look at this matrix, we find that we have only 2 elements in row 4, 2 elements in row 3. We can choose any one of them, because here this row has 3 and this row has 4. So, if you look at the ranking, this row has minimum, these 2 rows have minimum number of non-zero elements, we can choose any one of them. Let us choose this row as row 1. So, now we have ranked row 4 as 1 and row 3 as 2, that is the 4th row and column are now ranked as 1 1. So, this is 1 and this is 1. Similarly, this is 2 and this is 2, sorry, this is 2, and this row 3 is having 3 non-zero elements, and so this is numbered as 3. So, this is 3 and this is 3, and the first row has 4 non-zero elements, or the largest number of non-zero elements. So, this is 4 and this is 4. So, this is ranked 4 and 4. So, if we do this, then what do we get? We get the reordered matrix like this, that is, if we see this, now this is 1 1 and this is 1 4, because this is 1, this is 1, this is 2, this is 2, this is 3, this is 3, and this is 4, this is 4. So, this is 4th column and this is the first row. So, we have here 1 1 and then 1 4. Similarly, the other elements can be put like this, this is 2 and this is 2. So, 2 2, this is 2 1 is 0, 2 2 is 3, 2 3 is 0 and 2 4 is 10. So, 2 1 is 0, 2 2 is 3, 2 3 is 0, 2 4 is 10. Similarly, for other rows, that is row number 3 and row number 3 in ordered sequence. If we do, then we get the reordered or the ordered matrix like this, that is renumbered matrix like this. This we call the ordered matrix. Now, for this, if we do the Gauss elimination process as we did earlier, the matrix is now still the same matrix, except that the rows and columns have been ordered in a particular sequence. If we do this now, then what we find? We find that all the fill-ins which were all the 0 elements which were there are still 0 in case of this matrix. That is, these elements, if you see, these are all zeros which were there, and these are still remaining 0 while the factorization process goes on. That is, there is no fill-in which occurs in this case. Of course, this is not always true that there will be no fill-ins when we factorize the matrix. This is a special case, but in most of the matrices we will get fill-ins, but the number of fill-ins are going to be somewhat less as compared to if we do not order the matrix properly. Even this kind of an ordering, where we are ordering the matrix based on the valence of that row, is called a static or pre-ordering method, mainly because this ordering is done before the factorization process starts. That is, you see the matrix, you find out its valence for each row of the original matrix, and then you order them accordingly without going or looking into the factorization process itself. If we try to order these matrices at each step of the factorization itself, as the rows are being factored, then we have what we call a dynamic ordering. That is, a scheme in which axes are ordered at each step in factorization as per their valence is called a dynamic ordering, and is generally more efficient than the static or pre-ordering algorithm. This is very intuitive, because each time as we go through the factorization process, we are checking the valence, and since we are checking the valence in after each step of factorization, we are taking care of the fill-ins as well, and therefore, we expect that the number of fill-ins which will be caused by the fill-ins caused by the previous operations are going to be less, because we are taking care of the valence or the ordering at each step in the ordering process itself. So, a dynamic ordering is generally a preferred ordering method for sparse matrix problems. Next, we will talk about network solution by LU factorization. Till now, we talked about the Gauss elimination method. In fact, Gauss elimination method is quite efficient, but one of the problem with Gauss elimination method is that each time I need to solve A x is equal to b, I have to do the complete factorization process. In many cases, especially the case where the matrix A remains constant, this is going to be unnecessary overhead, that is processing the A again and again every time. Just like in fast decoupled load flow, we have B dash and B double dash matrices which are constant, and therefore, in each iteration if we have to go through the factorization process for the B dash and B double dash matrices, then we are having an undue overhead of computation. This can be reduced if we can store the matrix as factored matrices. The process is very similar to the Gauss elimination method, except that the process during elimination, the lower triangular part of the matrix which becomes 0 is used to store the numbers for processing of the column vector B for the operation, and this same thing can be looked as using the A matrix as a multiplication of two matrices, L matrix which is a lower triangular matrix with ones in the diagonal, and U as the upper triangular matrix, very similar to the matrix which we get after the Gauss elimination process. So, let us say we have a set of equation B is equal to A x. Now, this A matrix is n by n matrix. It can be B dash, it can be B double dash, it can be the Jacobian matrix, whatever it is, can be written as a product of two matrices L and U, where L is the lower triangular matrix and U is the upper triangular matrix. So, we have A x is equal to L U into x. This we can write as B is equal to L into x hat. Actually, this hat has not come here properly. This is x L into x hat, and what is x hat? X hat is equal to U into x. So, what we do is we write this as L into U x, and U x we are writing as x hat, because we will be working on a upper triangular matrix with x, and this will give us again a column vector x hat, and if we multiply it with L, then we will get as x is equal to where x hat will be equal to U x. So, this is what we need to do. So, what we will have do is first we will find out this in terms of x hat, and then B is equal to L x hat needs to be solved. So, what we do is B is equal to L x hat, we will solve to get x hat, and then we will solve x hat is equal to U x to get x. Now, how do we factorize this matrix? An efficient method to calculate L and U factors for a given matrix is triangular factorization algorithm. Now, in this algorithm, for k is equal to 1 to up to n minus 1, if a k k is equal to 0, then just go out, that is if the diagonal element is 0, then go out, otherwise you find out a I k is equal to a I k by a k k, and for I is equal to k plus 1 to n, that is this is the factored element. Then similarly, we can find out a I j as equal to a I j minus a I k into a k j by a k k, where I and j are from k plus 1 to n. So, this way we can try and get both the lower and upper triangular part of the matrix. Let us take this example of a 4 by 4 matrix. A x is equal to b. Now, here as we are doing the Gauss elimination process, what we do is we multiply this row with whatever value we had at this position, and then that is multiplied by this divided by this, and then subtract from this. So, this element will become 0 and we will get these elements modified. Same way we can make this 0, right, and for doing that we again multiply it by A 3 1 divided by A 1 1 and so on. So, this way we can again trying to make this 0 in Gauss elimination, but what we are doing, we are saying A I 1, that is these elements, is equal to A I 1 divided by A 1 1. This is what we are doing, we are dividing it by this and then subtracting. So, here we are storing this A 2 1 divided by A 1 1. So, A 2 1 after the first processing is equal to A 2 1 divided by A 1 1 for I is equal to 2 3 4. So, these okay. And A I j 1, these elements will become A I j, what was this, minus A I 1 into A 1 j divided by A 1 1. That is, we have this element which is I is equal to 2 in this case. So, A 2 1 into A 1 1 A 1 2 A 2 1 into A 1 2 divided by A 1 1. This will be this element and so on, this element and this element, all this processing can be done. So, what we are doing in Gauss elimination, these used to be 0, but now what we are doing is we are storing these elements there. Similarly, when we process this column, then we will have these elements stored again in the same fashion like this, and this elements will be what we will get during the factorization process. So, these elements are given by this. Again, when we process this element, so the third column when we are doing, we can process this. So, we will get these elements, this and this element, this element and this element here using the same relationship. And then if we do this, then what we have is we have a factored matrix here, where these elements, the upper triangular elements are same as what we get in case of a Gauss elimination, and the elements below the diagonal are the factors that we need for processing of the B vector or the vector of the mismatches, and therefore, this matrix now can be written as a factored matrix L u, where we have these elements of the lower triangular part of the matrix and the diagonal elements are 1, whereas the upper diagonal element of the matrix are denoted as u. The lower diagonals of course are 0, here upper diagonals are 0. So, this is the LU factors that we will get. So, we can use this LU factors for storing the factors of A matrix and use this for solution using the this thing. What we will do is we will work with B is equal to L x hat. So, we will calculate L is known, B is known. So, we will calculate x hat, and once we know x hat, we will solve for this x hat is equal to u x, and we will get x. So, this is how we do the solution. So, let the matrix remain constant, this B may keep changing, and we need to perform only these two operations, because this has already been done. This saves considerable amount of time in solving the large set of equations, and this is what normally is done for power flow solutions. So, with this we will stop today. In the next lesson, we will talk about how we can improve the computational efficiency further by using rectangular coordinate version for the voltage and admittance. That is, what we would try to do is avoid calculation of trigonometric functions, because when we are dealing with the polar coordinate version of the power flow, then we have sin theta, cos theta terms involved, and computation of trigonometric function takes considerable time on computer. So, in order to avoid these trigonometric functions, we will see how we can use the rectangular coordinate formulations to help in reducing the computation time. Then we will talk about the regulating transformers and how we can model them in a power flow solution, and then we will see some comparison of the NewtonRaphson load flow and fast decoupled load flow algorithms. So, with this we will stop today, and we will take up in the next lesson the other things as I discussed just now. Thank you very much.